is for you to hear. We are here to merge all sciences. So here we have master students in biophysics and we have PhDs in biotechnology. We have Dr. Jessie, who is a faculty in biophysics here, and she recently undergone a training as a radiation safety officer, and she stopped their exam in the atomic energy.
Atomic energy,
you
okay.
have a mixed crowd today, and I'll be shuttling in and out.
Okay.
The stage is yours. Please feel free to interact with him. Ask him as many questions as possible. I think that is what he likes the most. So the stage is yours for the next 5 days.
Thank you, Varsha. Okay, good morning, everyone. I'm happy to be here again. It's an honor to be re-invited. I'll tell you a little bit about myself before we begin, and then maybe we will do... Closer? How close? Like this? Maybe. Okay. Like this? Okay. Do you hear me now? Okay. So I'll tell you a little bit about myself, and then we will dive right in. We have a lot to talk about. So, as Varsha said, I was the dean until this Sunday. Now I'm free. No more administrative duties. It was really hard, 9 years. I'm in the School of Sustainability at Reichman University, which is Israel's only private university. All the rest are public universities. So it's a small campus, only 8,500 students, but we are proud to have the largest international school with 1,500 students from all over the world coming to Israel to study in English. We have an exchange program with 90 different universities. When we started GIAN in 2016, we were hoping to have an exchange program with this university, but somehow it did not mature. Hopefully, maybe this time it will. Because we see a lot of commonalities between Israel and India. Two very ancient cultures, but very advanced technologically and scientifically, with eyes on the future and on space. And so I will say a few words about my experience in space research. As Professor Keter mentioned, I was working with the Space Shuttle program in 2003 for the Columbia Space Shuttle mission. We had an Israeli astronaut on board as well as an Indian-born astronaut. So we did an experiment that was related to climate change and remote sensing of the atmosphere. You know, that culminated in a disaster in February 1st, 2003. But then, after a couple of years, I started working again with astronauts from different countries. In 2011, with a Japanese astronaut on board the International Space Station. In 2015, with Denmark, first astronaut. And then last year, with the first private astronaut mission by the company Axiom, we had a second Israeli astronaut that went into orbit to the space station, and I worked with him on the experiment, which I will share some data with you. I want you to help me with the analysis. I'm going to give you real data from space, and will ask you, if you wish, to help me analyze it, okay? And as we speak, we have another astronaut in the space station. He's from Denmark, same guy who went in 2015, and it was my plan that we will work as a class with him and send him forecast for thunderstorms all around the world. I will teach you how to do it, for him to observe with the camera from space. Unfortunately, European Space Agency delayed the observation that was scheduled for this Saturday. So we will just do a dry run as if we will send him a forecast. But normally this is ongoing research in space. So You know, and I will tell you, that somewhere on this planet there is a huge thunderstorm right now. The global rate of lightning on the planet is 60 strokes per second. Every second, 60 lightning strokes. Almost 1,000 or 1,500 thunderstorms occurring somewhere on this planet. Okay? So we are observing them from space, and it's one of the most fascinating, in my mind, a little bit subjective of course, fascinating topics in earth science, and it's related to so many different things, as I will show you in the next few days. I think it's related to the fact that life exists on this planet. Without the electricity of lightning in Earth's primordial atmosphere, it would have been very, very hard for life to emerge on this planet. And of course, when we study lightning, it's not only on planet Earth. We also look at other planets in the solar system, and we will get to that tomorrow or on Thursday, because, you know, we have the big questions of how did life start on this planet, and is it possible that life, biological life as we know it, will start somewhere else in the solar system, on other planets, and maybe in extrasolar planets, because you know we already found so many other solar systems outside our own. There are thousands and thousands of planets in the universe, just in our galaxy. So when humans are asking themselves, are we alone in the universe? Lightning plays a major role in the answer. My personal opinion is that we are not alone. But will we be able to ascertain this for sure? Will we be able to make contact with an alien civilization? That's a different topic. So, because I'm not sure about your background in atmospheric physics, I thought that I would start like with a baseline, really basic stuff in atmospheric science, and then we will just go a little bit deeper and deeper into atmospheric electricity. Okay. So, just a few facts about me personally. I was born, I usually give this trick to my students. I was born the same year that NASA was born. So figure this out. You can look up Google and see. Yesterday, October 1st, was the formal birthday of NASA. You just need to find out which year was it in order to know how old I am. I'm married. I have 2 daughters. One completed her PhD in microbiology. She's now doing postdoc. The other is doing her PhD, Tel Aviv University, brain science. My wife is also a PhD. She is a botanist studying invasive plants in Israel. So we are an academic family, you may say. And I've been living in a small town just near Tel Aviv. If you know where Israel is, Tel Aviv is right on the coast. We're a little bit east to the coast, but the weather in summer is not very different from Mumbai, very hot and humid. But the overall climate is very different. It's Mediterranean climate, which means short winters with a lot of rain and a lot of thunderstorms, mostly in winter, and then very long and hot summer. Half of the country is a desert. We are famous for desalination and trying to build agriculture in very dry areas. And I will tell you a little more about our country, my country, as we go along. I think it's one of those unintended consequences of GIAN program that the students learn on another country where the professor is coming from. And I hope you know that India and Israel are becoming really good partners and good friends in the last decade. A lot of collaboration, a lot of scientific, military, security, commercial, and of course many Israelis come to India to love the spiritual dimension of being in India. Okay, so that's the intro. And now let's begin. So let's start about atmospheric structure, just the basic. So this morning I checked the air composition. Not really, but these are the latest numbers. The air that you breathe, as you know, composed mostly of molecular nitrogen and oxygen, some argon, and most importantly, this gas, notoriously now the culprit in climate change. But notice this. So the number today is 420 parts per million, but this is an old pie chart. So the number is 350. It's quite old, not updated, because the CO2 concentration in the atmosphere, as I'm sure you're well aware, is continuously rising. Actually, from the Industrial Revolution in the 19th century, we've been pumping out into the atmosphere huge amounts of CO2 and other greenhouse gases, and we are actually changing the chemical composition of the air that we breathe. Okay? It's not becoming toxic per se, but the pre-industrial value was 280 parts per million, and today it's 420. 50% increase in slightly more than 120 years. That's amazing. That's amazing what humanity is doing to the atmosphere. We are actually emitting around 45 billion tons of CO2 per year just by existing as the human race with the economical machinery of producing energy, producing food, traveling around in cars, in planes, in ships. All this emits CO2, and although it's not the topic of this course, it's important to me, coming from the School of Sustainability, that you are well aware that humanity is on the brink of disaster. Well, many people say, you are scaring us. It's too scary, the future. And I always say, you know, the shape of the future depends on us. We make decisions now and in the coming decade that will affect the life of you and your children and your grandchildren in the decades to come. And certainly in Israel, we feel this already because the Middle East is one of the most vulnerable places to climate change on Earth. We are just on the border of a desert, and every small change in temperature and humidity really affects our life, and we already feel it. So in that context, Israel is striving to find innovative solutions, and it's known, or it used to be known as a startup nation. You know, I sent the book, there's a book, Startup Nation, so I sent copies of the book to all the students who were in the Gyan program in 2016. So if you behave, I will send you a copy as well. Anyway, so this is the issue of greenhouse gases, and I will not preach anymore about sustainability. I guess you know this. Being students, masters and PhD students, you have to know this already. And of course, there are many other trace compounds which are important in many other processes in biology. So how come the planet has an atmosphere? What is the source of Earth's atmosphere? We hypothesize that there are two main sources for the oceans and the atmosphere that our planet has. One is an external process, collisions with bodies in the solar system like comets and asteroids. and the other is internal process, like degassing from the internal Earth through volcanoes and volcanic activities. So when the Earth formed 4.5 or 4.6 billion years ago, actually it had a primordial atmosphere. But then through collisions and the emanation of gases from the Earth's interior, we built a robust envelope of gases around us that are kept close to the planet because of our gravity. Okay? So let me say a few words about comets, because it's a very interesting topic, also related, maybe, to the origin of life. And I will share, maybe you already know this theory, but it's, what are comets? We call them dirty snowballs. They're huge pieces of ice, frozen from the beginning of the solar system, and they contain many gases, carbon dioxide, carbon monoxide, and of course H2O, water, and they are located on the outskirts of the solar system, very far from the sun. And from time to time, they, by gravitational attraction of the planets and the sun, gravitate towards the center of the solar system, and they do this elliptical orbit. And when they approach the sun, the solar wind evaporates some of the ice, and it starts glowing. This is why we see those beautiful long tails. And it was long known in human history that when a comet appears, something bad is going to happen, mostly to kings and rulers. So ancient astronomers were actually in charge of predicting if a comet should arrive, because, you know, in astrology, any disruption to the order of the solar, lunar, and planetary cycles is considered a bad omen. That's the cultural aspect of comets. But we see that today the appearance of a comet is a very rare event, and all amateur astronomers are really excited. You can look up on the web. There are many, many networks that amateur astronomers buy telescopes and hunt for comets in the sky. And when they discover one, it's so magnificent. Of course, it's very hard to see from an area where you have light pollution, because you cannot see stars. But if you go to a dark place and you have a binocular or a small telescope, it's a wonderful sight. I'll tell you a little story about myself connected to comets. So when I was 12 years old, that was way back, I got the first astronomy book, and I read it. My father gave it to me, and there was this chapter about comets. And they said, Halley's Comet, which was last seen in 1910, will reappear in 1986. And as a 12-year boy, I was amazed. How do they know this? How can they predict the future so precisely and know that this object will reappear? And so I said, okay, I got to get down to the bottom of this. And so eventually, that small astronomy book led to my choosing a career in physics and in science. I had to figure this out. And I understood how it was calculated. And so my lesson from this is I call it the magical age. When you will be parents and you will have children, there's a small time between the ages of 10 and 12 maybe, or 9 and 13, maybe it shifted a little bit, that you can affect your child's interests and maybe future decisions. And if you want them to talk about science, then this is the correct time. Anyway, that's about me. So we know there were a lot of comets in the past. There's a huge repository of comets outside the orbit of Pluto, really far away from the sun. So if this is the solar system, like a zoom in, all those dots that you see are frozen debris or frozen ice from the beginning of the solar system. Very ancient. It's actually as if there was a freezer that stores all the materials that were in the solar system when it began, when the sun evolved and the planets. So from time to time, such a comet falls into the inner solar system and may impact Earth. Okay? And this is a recent comet. You can see how beautiful it looks. The head and the tail always point towards the sun. Okay, so this is sunset, and you can see the sun already below the horizon, but the solar wind takes the gases away from the ice. And why did I say that comets may have been related to the beginning of life on this planet? Because we have discovered many organic compounds in the gases of the halo and the tail of comets. So we know they have organics. And when those organics have been imported into the ancient Earth, bringing water and other gases, but also some organics, they may have formed what we call the primordial soup. You know about this theory, the Oparin theory about how life may have started on this planet? I'll get back to that shortly. We call this theory panspermia, as if the origin of life came from space, like it was inseminated by comets. And it's a kind of a curious idea, interesting, was put in the 1960s by a British astronomer, Fred Hoyle, but is supported by evidence. We know that comets have organic molecules which may have been essential for the emergence of life on this planet. And we can actually see trails of the comet material enter Earth's atmosphere at certain times in the year, because some comets are, as I said, repetitive. They come back every 76 years, like this is Halley's Comet, so 1910, 1986, maybe 2062, next show, if we will be here. But every time the comet sheds a little material in its orbit, and when the Earth intersects the comet's orbit, it collects cometary dust. And this dust actually falls down, trickles down from the atmosphere all the way to the surface. We can collect it, we can look at it, and we can analyze it, and we can take it to a scanning microscope and see the mineralogy and the biology of those ancient materials. So last month I was at a meeting in Japan, big science meeting, and I went to a session which was not directly related to discoveries, to new discoveries. It was about women in science. And very prominent lady researchers gave talks, and then there was a talk by a gentleman, an elderly Japanese gentleman, and he told his story about his grandmother. And his grandmother was a housewife that lived in a big city in Osaka in Japan, but she was fascinated by astronomy from little age. And I'm talking about the beginning of the 20th century. That's 1905. At that time, girls were not allowed to go to high school, not to mention university in Japan. But still, that girl had a dream about the sky and the heavens and all the planets and comets, because her father told her stories about ancient mythologies and constellations, you know. Anyway, she was a mother of 5. And when she grew up, after being a housewife for so long, she decided she wants to come back to science. And what she did was collect dust in the backyard of her house in Osaka. And most of the dust was from urban pollution, but some of it was actually from comets, from ancient comets. And she did that every night. She went out after completing her chores as a Japanese housewife in the 1920s. She kept a diary. She made measurements. And then, for many, many years, she collected a huge amount of data. She approached a lady scientist at the University of Osaka, gave her her observations, and suggested that the first Japanese mission to Antarctica should collect dust in Antarctica from meteors and from comets. And he told the story very emotionally. It's very rare to see Japanese people expressing emotions in public. And then he said, that was my grandmother. And everybody, gave him a standing ovation, because it was clear that his grandmother actually affected his choice to do a career in science, from simple backyard astronomy, collecting dust in the backyard, just doing basic science, collecting data. I think it's a huge lesson for everyone, that you can do science if you just are motivated and curious about it. So, a small story about cometary dust. So humans are preoccupied with comets not only for the cultural aspect, but also because comets not only brought life to this planet and the essential ingredients, they may also pose a grave danger. Because nowadays, if you think about it, if we have a cosmic bullet coming, a huge comet colliding with the Earth, that can bring maybe catastrophic outcomes to humanity. Okay? So NASA is and the European Space Agency and JAXA as well. I'm not sure if ISRO is already planning a comet mission. Maybe it does. But we have to figure out how strong comets are, what is the structure of the ice, and if there is one comet predicted to collide with our planet, can we avert this danger? So, another fun fact about me, I'm a buff of science fiction movies. Do you like science fiction? Any of you? Do you know the film Armageddon with Bruce Willis? You've seen it? An old one. But anyway, in that movie, we have a danger, an asteroid or a comet is coming. We have to blow it up, right? But in order to know if this is even possible, you have to know what it is made of, okay? So NASA and the European Space Agency are very busy trying to explore what comets are made of, how strong they are, and if, God forbid, there is one coming to collide with the Earth, and that's already happened so many times in the past, as we know, can we actually fight it? So there was this Rosetta mission that was supposed to land safely on a comet, take a sample, and maybe analyze it. And it was planned, it was a mission that was planned for 20 years. The scientists and the rocket planners, everybody was busy until this rendezvous was supposed to occur, but go back. Finally, in the last minute, the lander that was supposed to land on the comet was on the surface of the comet, but it hit a rock and fell on the side, and so the antenna that was supposed to broadcast all the data was broken. Nothing, no success. Imagine planning a mission for 20 years and then in the last meter of this cosmic journey, everything goes down. And I thought to myself, I suppose there were so many master and PhD students waiting for the results from that mission, and now they have a big problem trying to find a new topic for the research, but that's a side thought. Anyway, comets are important. Comets are still with us, and from time to time they appear close to the Earth, and we have to watch for them. And as I said, they brought the atmosphere, they brought the oceans, and they brought minerals and organic compounds. So the other source for Earth's ancient atmosphere is volcanic eruptions. On any given moment, we have approximately 100 active volcanoes on Earth. You can actually find them on the web. There's a big website by United States Geological Survey, USGS, that keeps track of all the active volcanoes. Because volcanoes not only emit gases and dust and ash, they can be really dangerous. There are no active volcanoes in India right now, but there used to be huge volcanic activity here in this subcontinent. The Deccan Traps in central India are probably very ancient remnant of massive volcanic activity 500 million years ago, which emitted huge amounts of gases, water vapor, and nitrogen and carbon dioxide, sulfur dioxide. So this goes on and on. The Earth slowly but continuously lets out gases that are stored in the mantle, in the deep layers of the Earth. So it comes from a deep magma chamber usually, and then goes all the way up, and through the volcanic conduit, it can go up and erupt into the atmosphere. Sometimes these eruptions are so strong that we can actually see them from thousands of miles away from where the volcano erupted. For example, in 2021, January 2021, there was a submarine volcano eruption below the ocean water near New Zealand. Maybe you've heard about this. The eruption was part of what we call the Ring of Fire. This is the area where you have the most active volcanoes on the planet. So it was somewhere here, and the explosion was so hard, so strong, that the cloud of ash reached 50 kilometers through the water all the way up into the upper atmosphere, and the shock waves spread around the planet. It was an amazing event, and it was actually caught by satellites in real time. They could actually see the mushroom cloud go from below the water all the way up into the atmosphere. And of course, we know that when Earth was young and violent, it had many, many, many more volcanoes compared to today. Today we have 100, but back then we had thousands active volcanoes that emitted continuously gases. Now it's more rare. It's usually in the news. If you have a big volcanic eruption, you have TV people going all the way and taking images and pictures, but they're actually very dangerous. So if you want to know how, there are some people, I would call them crazy, but they go really, really close to the crater and just take measurements and do imaging. And if you guys have Netflix, I can recommend you a very good documentary which was on Netflix. It's called Love of Fire, The Love of Fire. It was about two French geologists, a husband and wife, and their specialty was imaging of active volcanoes right on the crater, right on the mouth, and you could see the lava streaming and all the gases. Eventually they were killed in a volcanic eruption in Japan. They were not quick enough to escape when the volcano erupted, but I highly recommend it. It's an amazing visual journey to see how volcanoes look from real close. So, to conclude this part of my talk, I give you this very famous, not to say iconic image of the Earth. It's called the blue marble. Have you heard this term, the blue marble? You know what marble? Marble are like you play with them as a child. So this blue marble was taken by the astronauts of Apollo back in 1972 as they were flying from the Earth to the moon. And they looked back and they saw the sunlit side of the Earth, and what you can see is the beauty of the planet, right? So beautiful. Antarctica, Africa. This is actually the Arabian Peninsula, and my home country is right there, right on the top. Israel is here, okay, and India is probably here, not so far. 6 hours flight. Madagascar, Africa. Let me ask you, what don't you see in this picture? What don't you see? You don't see borders, okay? There are no borders that you can see that we draw artificially between nations and between peoples, but you actually don't see any sign of humanity. It's a day side. It's a day side, so you don't see the city lights. If it would take it on the night side, you would see humanity in the full blast. You would see the light of our major cities. And I urge you to look up, there's a famous, I have it in my office, it's called Earth at Night. It was composed of many, many, many satellite images of the Earth at night with no clouds. So you just see humanity. You see the lights, you see where humans live. And India, by the way, looks like a big, big, very dense point of light on Earth. And Africa completely dark. So it also tells you a story about energy, about technology, about humanity, just by a single shot from space. And I think when people saw this picture in the 1970s, it kind of initiated one of the most important environmental movements in the 1970s. People were looking at the Earth as a system of systems. Everything is connected. The atmosphere, the clouds, the oceans, the Earth itself, the solid state of the Earth, the ice in the poles, all these kind of interacting spheres within the what we call the Earth system science. And maybe you've heard about this in a more, I would say, spiritual manner. Was called the Gaia hypothesis. Gaia, the ancient mother of all living creatures in Greek mythology. So the Gaia hypothesis was that Earth, as a system of systems, is in balance in order to support life. It supports the existence of life on the planet. And what happens now, coming back to my point on climate change and sustainability, we are disrupting Gaia. We have took the balance, and because we changed the composition of the air, we changed material cycles in the atmosphere, Gaia is now not in balance. And we see this in many, many appearances, natural disasters, huge amounts of storms, and of course, lightning, as I will show you later. So, iconic picture. Okay, so we'll take a break in 5 minutes. I just want to usher you into the next topic and ask you this question. So we know that Earth at the beginning was very hostile. It was hot, volcanic eruptions, and collisions with planetary bodies, and no oxygen in the atmosphere, obviously, lightning in the atmosphere, clouds. How did life start on this planet? Do you know? I mean, we don't know the answer for that, but we have some theories, okay? So, from this initial state, the emergence of life on this planet and maybe on other planets was a gradual process, but actually, if you look at it, it was kind of fast, because when the Earth cooled and oceans started to accumulate on the surface, it took just 700 million years, and we already have unicellular life here. Most of you study life sciences, so you know this. The ancient microbes and very early life forms appeared very quickly on the Earth, which gives us an idea, maybe, on the existence of life elsewhere in the solar system. But how this occurred from this kind of initial state to go to this, where we have self-replicating molecules, like the double helix. You can teach me of that. I'm not a biologist. You probably know more than me about life. But it was quite, in relative terms, very quickly that life appeared on this planet. And we still have ancient life forms in some places on Earth until today. We call those stromatolites, and they are 2.7 billion years old. So it's kind of unicellular cyanobacteria colonies in Australia and in many other countries. And they are the most ancient life forms on Earth. And those creatures started by their sheer existence to modify the composition of the ancient atmosphere. Okay? And they started doing photosynthesis, taking CO2 out of the air, converting it to oxygen. Slowly, slowly, the amount of oxygen in the atmosphere increased until it was high enough to create the ozone layer, the shield that protects us from UV radiation and from cosmic radiation coming from space and from the sun. And life created the shelter that enabled life to prosper and emerge very quickly. So it was those initial creatures that lived here on this planet that built the initial layer that protects us and enabled life to prosper. And we call this the Cambrian explosion. And you can see that this is the this is the concentration of oxygen in the atmosphere compared to the age of the Earth. Okay, 4 billion, 3 billion, 2 billion, 1 billion, and this is today. So today, as I said at the beginning, we have like 21% or 20.9% of molecular oxygen. Back in the past, when there was no oxygen at all, but it gradually accumulated, and we can think and see the emergence of many, many life forms on Earth when the oxygen level was high enough to create the ozone layer. So just briefly, I'm sure you know this, the ozone is generated by the interaction of solar UV with molecular oxygen and is destroyed by absorbing UV and being decomposed back to molecular oxygen. And this cycle is in balance and creates a level that protects humans and biological life from the harmful consequences of UV radiation. Okay? That occurs between 15 and 40 kilometers above the surface of the Earth, what we call the ozone layer. It's not really a layer, it's just a region in the air where you have a lot of ozone. And I'm sure you've heard about ozone depletion and the hole in the ozone layer, which was caused by CFC, by chlorofluorocarbons, and the way humanity, when discovering this danger to the ozone layer, international treaties were signed very quickly in 1985 and 1986 in order to stop the destruction of ozone. And 40 years after those, 30 years after those initial agreements were signed, we see that the ozone layer is recuperating. And in my mind, this is a very good and positive sign when we want to tackle global problems, that if humanity unites and works together, we can solve really big problems. And my friends always say, oh, you're such an optimist. You think we can solve climate change the same way we solved the ozone layer crisis in the 80s. And of course, it's a different magnitude of a problem, much larger, many, many stakeholders, many players, but still, I think we can fight this. But anyway, the ozone layer and the emergence of the ozone layer enabled life to flourish. Okay, so this is basic stuff, you know it, but we call it the Cambrian explosion. Like 500 million years ago, suddenly the amount of biodiversity, so many creatures appeared almost simultaneously on Earth. And this is a paper from Progress in Biophysics and Molecular Biology, a journal I'm sure some of you already know. But this is a very interesting paper, and it poses the question and tries to answer why at that specific era in the geological history of our planet, suddenly so many life creatures and forms appeared. Was it caused because of comets, or was it just the rise in the level of oxygen in the planet? And you can see that the number of different life forms just exploded exponentially 500 million years ago. Suddenly you see so many different fossils, so many creatures. So this paper concludes that it was the rise in the oxygen level. when we reached the threshold of 3% molecular oxygen in the air, ozone layer was generated, and suddenly life could come out of the water and thrive on land. They had already this dome of protection above them. So, a short history of life on this planet, very related to, as I said, the emergence of oxygen. Okay, and we know this because we have all the biosignatures of fossils that we can actually carbon date and use different radioactive elements to pinpoint the exact age of when this happened on our planet. And you can go and do this geology reconstruction and find out the exact age where life began to explode on this planet. Okay, so I'll stop here. Let's take a break for 10 minutes, okay? So you can have some tea and water, and then we will resume. Okay. Yeah, take your 10 minutes.